Welcome everyone to this first talk of Indu's seminar series. So I'm really very excited to introduce our first speaker, Ms. Ketaki Deshpande. So before I start, I would like to request all of you to please disable your camera and mute yourself, at least during the talk, because we are recording this session. And also, if you have any questions, please use the hand raise option. Then I'll ask you one by one to ask the questions. So now let me introduce our speaker, Ms. Ketaki Deshpande. She is a second-year PhD student at KU Leuven and the Royal Observatory of Belgium. She is currently doing her research under the guidance of Professor Yasmina Magdalenic and Dr. Luciano Rodriguez. The focus of her PhD revolves around radio diagnostics of coronal plasma with novel in-situ observations and modeling with EUHFORIA. Ketaki completed both her bachelor's and master's degree from Savitribai Phule Pune University. Following her studies, she undertook an internship at the Indian Institute of Astrophysics campus, which is Gauribedanur Radio Observatory, where her profound fascination with radio solar physics took root. So her dedicated work during this internship resulted in 2 publications, which is very impressive. Motivated by her experience, she embarked on a PhD journey in the same research field. Now, she also got the award for a PhD grant for pursuing her research in the Royal Observatory of Belgium. So with that, I would like to invite Ketaki. So Ketaki, please go ahead. The floor is yours.
Thank you so much for a nice introduction and giving me this platform to share my work with you all. I'll share my screen with you.
Yeah, sure.
I hope you can see my screen.
Yes.
Yeah. Yes. So hello everyone. Again, my name is Ketaki Deshpande, and today I'm going to talk about estimation of electron density with radio observations and comparison with novel Parker solar probe observations and EUHFORIA simulations. So this is the overview of my today's talk. I'll first talk about the motivation behind this work. Then I'll briefly introduce about the solar radio emissions, which is the main part of this work. And then I will talk about the type 3 radio burst, which is the focus of this study. And then I will talk about the gonio-polarimetric observations and the method of radio triangulation. I'll talk briefly about EUHFORIA, and then I will talk about the selection criteria for the event selection. And then I will discuss in detail the events that I have studied, and lastly, the conclusions. So what is the motivation for the study? So the properties of solar wind and CMEs were up to now poorly considered by in-situ observations. So we only had in-situ observations closer to the Earth at approximately 1 astronomical unit distance. So which was very inconvenient to study the phenomena like solar wind and CMEs and evaluation of them. So, and also the models of solar wind and CMEs, such as EUHFORIA and NWAVE, which are like highly dependent on the input parameters that we give to them, and do not provide prediction of the disturbance arrival with sufficient accuracy. But now, as we have this newly launched spacecraft such as Parker Solar Probe and Solar Orbiter, we have in-situ observations at various distances from Sun to Earth. And that is why this is the correct time to study this kind of thing, which can allow us to validate the results obtained with both radio observations and modeling. So Parker Solar Probe, PSP, and Solar Orbiter gives us a very nice opportunity to validate all the observations, remote sensing observations, and also the modeling. So as I studied, solar radio emissions is a main part of the study. So I will briefly talk about that. So what is solar radio emissions? Is the emission in radio wavelength. We have different types of radio emissions, majorly 4 types: type 1, type 2, type 3, and type 4. So type 1 radio burst are due to the non-thermal electrons associated with active region. You can see it here, which is they are generated close to the surface of the sun. And then we have type 2 radio burst due to the fast electrons accelerated at the shock fronts. Type 3 radio burst, which is the main focus of this study, are due to the fast electron beams propagating along the open magnetic field lines. And lastly, type 4 radio burst due to the electrons in closed CME structure. So the study of solar radio emissions can give us a lot of information. Like we can get to know about the coronal plasma properties such as coronal electron density, Alfvén velocity, magnetic field strength, shockwave velocity, etc. And that is why it's very important to study solar radio emissions. So as I said earlier, there are mainly 4 types of radio emissions, and they are mainly basically are divided by their types by looking into the dynamic spectra. What is dynamic spectra? It is a frequency versus time plot. And I have shown you here a dynamic spectra in a low frequency range, which is what I'm currently studying. So here you can see different types of radio emissions. First is this type 3 radio emission, which is a fast drifting structure that appear on the dynamic spectra. If you see the timeline, you can see that it's a very high fast drifting structure. And then we have a type 2 radio burst, which is a slow drifting structure that appear on the dynamic spectra, which is associated with the shock fronts. And we have a type 4 radio emission, which is like a continuum. You can see it here. And to just show how radio emissions we can see in the dynamic spectra, it's like this. So when we are observing in the high frequency, we are observing closer to the sun. And as we go away in the lower frequency, we are going away from the sun. So that is how we say high drifting structures in the dynamic spectra. So this is a short movie to just show like how the dynamic spectra actually looks like. So as I said, the main focus of this study are the type 3 radio bursts. To just summarize again, they are the signatures of fast electron beams traveling along the open or quasi-open magnetic field lines from the sun to interplanetary space. Sorry. These are the most frequently observed type of radio bursts. So whenever you see dynamic spectra, you observe type 3 radio bursts most of the time. And generally, they are considered to be a plasma emission, which is a coherent emission mechanism. So here you can again see that in the dynamic spectra, we can see a type 3 radio burst. So I have used to study these type 3 radio bursts, a particular types of observation, which are goniopolarimetric observations. So the main goal of this goniopolarimetric observation is to retrieve direction of arrival of incident electromagnetic wave. So we can retrieve theta or co-latitude and azimuth with this goniopolarimetric observation. So there are 2 types of goniopolarimetric observations depending on the type of the spacecraft. So for example, for wind, we have spinning antennas, and therefore we use spinning modulation measurements. And for stereo, we have fixed non-coplanar antennas. That's why we use instantaneous measurements. You can find more details about this observations in this following references. So now we have goniopolarimetric observations, and with those goniopolarimetric observations, we can get wave vectors. And with these wave vectors, we can use the method of the radio triangulation to estimate the radio sources. What are radio sources? The radio sources are the regions from where the radio emission is coming from. So the wave vectors obtained from the direction finding observations from 2 or more spacecraft. So we need at least 2 spacecraft for the method of radio triangulation, which will allow us to locate the source position of the radio emission. So we define the radio source position as the region between the shortest distance between these 2 wave vectors. So you can see here I have stereo A and wind, which provides us goniopolarimetric observations. We can get the wave vectors from them, and the shortest distance between these 2 wave vectors, we define it as it is a 3D region. So here in this diagram, you can only see a 2D version, but it's actually a 3D space that we define as a radio source position. You can again find more details about this method in this following references. Another part of my study, which is also very important, is EUHFORIA. EUHFORIA is European Heliospheric Forecasting Information Asset, which is a space weather form modeling tool that computes the time evolution of the inner heliospheric plasma environment. So EUHFORIA mainly consists of 2 domains, coronal domain and inner heliospheric domain. Coronal domain is up to 0.1 AU, and inner heliospheric domain is from 0.1 AU to 2 astronomical unit distance. We also have a third part, which is a CME insertion. So we can, if we have a CME, then we can insert that CME into this model as well. But for my study, I don't have any CME associated with my events, so I mostly focused on the solar wind model. The particular thing about EUHFORIA is that we can actually change our kernel model with different. So it's very flexible. So if you want to change your kernel model, you can change that, and you can have the flexibility in your space weather modeling. So we have like default kernel model, multi-VP, awesome, such kind of models. So for my study, I mainly focused on the default kernel model. You can see here a 3D diagram that is obtained with EUHFORIA. And this is for velocity. You can see a color coding with different kind of velocity. So you can see higher velocity in the, I see someone has a question.
Yeah, what do you mean by a default coronal model?
Default kernel model is like I have no, I don't have much information about multi-VP and awesome, but I can tell you about the default kernel model. Is that in this model we are using PFSS for getting the magnetic field, and also we have this SCS, that is a Shatton current sheet model. To like combination of these two we are using, and we also have the measurements for like real measurements of density and velocity. So it's combination of this and that we say as a default kernel model. I hope I have answered your question. Okay. Okay, I'll go ahead then. So I was as I was saying, this is a 3D diagram obtained with EUHFORIA, and you can see a higher velocity, high velocity wind coming from the polar regions, and slow solar wind coming from the equatorial region, and we have this gray thing as a heliospheric current sheet. Like this, you can obtain a nice 3D visualization of the solar wind. So for this study, I needed to study type 3 radio bursts. For that, I need to select them, and to have that, I have certain selection criteria. So what I did is I only selected the type 3 radio burst which were observed during the PSP perihelion passage. Why is that? Because when we have the PSP perihelion passage, so PSP is approximately at 20 solar radii from the sun, which is the region where we have this interplanetary type 3 radio burst, you can say, or the low frequency type 3 radio burst. So which gives us a opportunity to compare the densities obtained with the radio observations and density measured by the PSP. Then second criteria is that the type 3 radio burst should be observed by at least 2 spacecraft, which is very important because for the method of radio triangulation. If we don't have measurements by 2 spacecraft, then we can't do the radio triangulation and we can't obtain the 3D radio sources. Third criteria is that the emission needs to be significantly stronger than the background emission, which is very important for accurate results. And if possible, they should be isolated from the other radio bursts. So these were the 4 main selection criteria for the type 3 radio burst. And I have shown you one example of the selected type 3 radio burst. So you can see 3 groups of intense type 3 radio bursts, which are in my catalog, which were observed on the 5th of April 2019, which is the second PSP perihelion. And for one of them, I have shown you the spacecraft positions. So you can see that wind, which is near closer to the Earth, of course, and stereo A are separated in almost 90 degree, or you can say quadrature, which is also a very important criteria to have good results in radio triangulation. And also we have PSP in between these 2 spacecraft, so that if type 3 radio bursts are propagating in this in between them, then we can actually compare them with the PSP observations. So the first event that I studied, as I've shown in the dynamic spectra as well, is the 5th April 2019 event, which was observed at 120 UT. You can see two spectra, one with stereo waves and with wind spacecraft. And in the dynamic spectra, you can see that stereo waves observe multiple type 3s, but wind only observed the 3 intense ones. And I try to get the time profiles from stereo and wind. So I have only shown for the stereo, but we similarly obtained with the wind as well. So you can see that if we plot the time profiles, then we have majorly two groups of type 3s. The first one is the isolated one, or you can see only one single peak in the time profile, which indicates that we only have a one type 3. And in another thing, you can see two peaks in the time profile, which indicates that we have two type 3 radio bursts present. So in time profile, we can only identify three major type 3 radio bursts. So we have only studied this major three type 3 radio bursts. And to again mention about these type 3s, they are generated by these jet-like structures which accelerated electron and which caused to generation of radio emission. So this active region was slightly behind the east solar limb. You can see this active region 12738. And this active region actually produced many type 3s afterwards also. Like you can see in one paper, which is Wang et al. 2023. In that paper, they have mentioned that this active region has produced a lot of type 3s that was studied by different authors. I also did the comparison between what we see in stereo and wind and what we see in Parker-Solar probe. So this is the dynamic spectra obtained with Parker-Solar probe, and you can see that in Parker-Solar probe, which is a very high resolution data, especially during the PSP perihelion passage, compared with stereo and wind. So we can see that there are multiple type 3s that we can see it here if we have a high resolution data. And also sometimes we can see this fundamental and harmonic pair as well. This is very important to know because when we are triangulating our radio sources or estimating radio sources, we need to know like what we are triangulating. This is very important to see like what like this region that we are getting where the radio emission is coming from is for which type 3s. So this is very important. So these are the results with radio triangulation. So this G1 that I say like for group 1 type 3, which was the isolated type 3. So for this type 3, we could obtain nice radio sources, and this shows a nice propagation path, which was slightly going downward. But for other two type 3s, we could not get much radio sources, and we were restricted for the few frequency pairs because of their appearance in the time profile as well. Because after a certain time, they just appear as a one single peak and not two single peaks. That's why we have very few frequency pairs. And also, there were like multiple type 3s or their close proximity towards with each other. We observed that there was a mixing of signal, and due to that, the estimation of the radio sources was not accurate as we see in a case of isolated type 3. So this is just to show like how the propagation of this type 3 or the path of the propagation looks like. Then we obtained distance between the wave vectors, which is, we can say, the size of the radio source, how that is dependent on the frequency. So you can see that as we go towards the lower frequency, the radio source sizes appear to be increasing. But if we closely see that, then they are mostly below 15 solar radii. So this is also one thing that I need to study further, that if it is the case for all the type 3s, that they are restricted mostly in the same region and not very much dependent on the frequency. That is one thing I need to study further as well. But this increasing of radio source sizes with the frequency is well studied in the Saint Hilaire et al. 2013 paper. So I need to study further and see like how this is actually dependent on the frequency. Then as we obtain the radio sources, so we have different heights now. So for each frequency, we have estimated from which height the radio emission is coming from. So we have this nice relation between the plasma frequency and density. So we can obtain radio densities with that. So what we have done here is this color coded points are the densities obtained with radio observations. So each color represents a different frequency. So this black solid line is the density obtained with Parker-Soroprov, which is the in-situ density. And this colored colored lines are the model density with EUHFORIA. This green solid line is the density modeled with at the PSP position. So this is if you see that, sorry. If you see this, then you can see that at least at the when we model the if we model the density at the PSP position, then it looks underestimated. So, and also we have this radio densities which are higher in order compared to the in-situ density. So we have a lot of discrepancy over here. But this is the preliminary results that we have. So second event was also on the same date, but at 20:05 UT. Again, we have the time profiles for the same, and same as the first event. We just in the first group we see the complex time profile. We see two peaks over here, and for the second second time profile, we only see one peak, which says that it's an isolated type 3 in which appears in our time profile. And again, the same active region was responsible for this type 3 radio emission. Again, I compared that with the PSP, and we again see here multiple type 3s present over here. So the high resolution data is really important to see like what really is in the dynamic spectra. Again, the results with the radio triangulation. And for this event particularly, we actually noticed the mixing of the signals. So here you can see for this particular type 3, then you can see for the higher frequency, the radio sources are not exactly accurate. They are not going towards the sun, but they are going away from the sun, which is inaccurate. So this behavior we noticed because of the subsequent burst or the burst which are in close proximity. Because of that, when we get the Gaussian polarimetric observations like theta and phi or full latitude and azimuth, they are fluctuating very much. And because of their fluctuations, we cannot get a very nice position of the radio sources. But when we see for the isolated type 3, we get a very nice propagation path. So again, to show that how we get the inaccurate radio source position. And this is very important for estimating densities as well, because if we could not get a nice radio source position, then it's very difficult to estimate that from which density we should compare with. Yes, someone has a question.
Hi, Ketaki. So
Yes.
I had a doubt about the wave vectors. So they must be affected by the propagation in the medium as well, right? So the spread you see, much of it should be affected by that as well, right?
Yes, you mean scattering.
And the different magnetic field structures through that they pass, so that will keep shifting your source, right?
Yes. So one thing is this event was particularly during the 2019, which is very close to the quiet sun period. And also, as we see, that's why I have showed you the distance between the wave vectors. So again, here I can show you that.
But it may not depend on quiet or active, because it's because of the emission mechanism itself, right? It's produced
but
to the plasma frequency. So
yes, but that's why that's what I'm trying to show you here, that even if we have like different like as you see as you say that we might have like scattering or something like that, but that's what we are trying to show. Like here, if we see that like for some things on the higher frequency here, because of the subsequent burst or the close proximity in the burst, we see that in the higher frequency we are not getting the accurate source position, and that reflects in the distance between the wave vectors as well. They are much higher. But if we in general consider that they are only restricted in a certain band, so which is like till 25 solar radii. So
but these are two
not...
different effects, right? So the first one is mixing of different things,
Yes, exactly. So,
events, and
yeah.
the second one is scattering alone can give you probably that much, right?
Yeah, but that's what I'm trying to say. Like the scattering cannot be that cannot play that much important role, because you can see it here. They are just in band. They are not very much fluctuating also. So, but we only have 2 events, so we need to actually have a lot of statistical data as well. So I have
But
like
what is this very
No,
much
this
fluctuation? How do you define the very much fluctuation? So I
but
can
this could
spread actually, right?
this could be because the frequency is also observing frequency is also low, and compared to that, the bandwidth that she's looking at, if you look at the band separation, that is also low. So I don't think you will actually see a large variation there because of the low frequency.
Exactly, yes. So that was also one point, because the observing frequency is from like 400 kilohertz to approximately
You're not
6,000
very well
kilohertz,
separated in
and it's
you're not
very,
very
like,
well
small,
separated
yeah.
in frequency to actually see the variation
Yes.
of scatter.
Yeah. Yes, I'll go further again, and we again compared the densities like the first event, and we got the same results. So the major thing that one should notice, as even if we model the density at PSP position, which was underestimated, which should not be the case, because we are modeling the density at the PSP position. So to decrease this discrepancy, we change certain input parameters in our coronal model, that is PFS source surface radii. So we did simulations from 2.6 to 3.0 solar radii. And we noticed that if we do the simulations after 2.9 solar radii and further on, then we get the same results. And with that, we actually could manage to get that in one order. So obviously, we cannot see the fluctuations that we have in PSP in-situ data, but at least it's of the same order as the in-situ data. So now this green solid line, which is the density model at the PSP position, is actually matching the order of the in-situ density. Yes.
Now, again for the same point, do you then require a measurement every 100 kilohertz? Because you are definitely not going to see a variation.
What we have. So we have like certain frequencies that we have with stereo and wind, and we could not go further than that, and that's it. Like, so whatever we have to use that. But if we have like a lot of frequency pairs, then it will be great. Then we can do much nicer things.
And what is the so can you go to the previous plot where you show the scatter plot? Ah, yes. So what is the error in the measurements?
So that's what
you don't have an error bar there.
Yes, exactly. I haven't actually done that, but for this only, like I would say that, because for each frequency pair, we have multiple points. So this only shows the error in the estimation, because each flux value, you will have one theta and one phi value. So we have done that for different several points, and we can see that for each point there is a like different distance between the wave vectors, and this in total gives you the area from which the radiation is coming from. So indirectly, this is only showing how much is the error. But yeah, I haven't actually plotted the error bars here as such.
The classical way of estimating the error bars in the triangulation and direction finding provides results which really like huge errors, which would not allow you to trust your results at all. So the way this is done presently is not adequate. This is why Ketaki doesn't show it. What is shown is the spread of the possible values, which is the minimum error which you could expect to have, because the source is somewhere between these two wave vectors, which means the sources can be at least as large as the distance between the wave vectors.
So one can say that these are the maximum.
Yeah, kind of. It gives the indication of the source size. And yeah, I have written here, I don't know if you have read. So as we going to the lower frequencies, we would expect, if the scattering is the dominant process, to increase strongly the error. And what was shown here is that actually for the higher frequencies, the spread of the values is much larger than for the low frequencies. And so it's in contradiction, and it shows that the scattering is not the one which produces this big spread of the values, but actually the problem is that the method doesn't, and the observations do not manage to distinguish between signal coming from the two different places, which kind of gives this big source size.
I agree with the scattering point, because again, like you mentioned, so it's probably I don't think you should really expect to see a large scattering effect with such a small band, especially at kilohertz frequencies, because the frequencies are not too well separated. So you would probably see it, for example, if I look at a 10 megahertz observation and compare it with 1 megahertz, I might see something, but I don't think I would expect to see anything at 1 megahertz and 500 kilohertz.
In principle, you would expect to see it, huh? So you would still have to see the
it's there, but it's not really frequency separation is not large enough. The scattering is there, but the frequency separation is just not large enough to show noticeable difference.
Yeah, I think it would be in the same scale height, right? That's what you mean, right?
Yeah. I mean, some of the studies by Bratislav Krupar still show that the distance between the wave vectors indicate a strongly increased source size, which he attributes to the scattering, which, so he kind of measures it, but I'm not fully convinced enough.
No, we agree that there is scattering there at this low frequency. There's no doubt about it. But what we are suggesting is, you wouldn't really notice the difference at such a small frequency scale, range.
But it's not. No. I mean, I would not agree with that, because even if the changes between 1 megahertz to, like, say, 600 kilohertz, you are still attributing this to the very different distances from the sun, which means you will have a plasma characteristics which are significantly different. So the scattering should change.
But if I can add one thing, that Mina, so you have a density model in place, right? So you can probably also estimate what is the scale height within these frequencies, right? So if it is within the same scattering screen width, given the propagation group velocity or something, then it would be the same. Right?
The group velocity does not really change as much.
So that can be checked because you have a model, right?
I mean, it can be checked because basically the position of the radio sources is a 3D position, which does not forces you to put any density model there. You can estimate yourself a density model, taking into account that it's a plasma emission. So indeed, that's something which can be checked.
I guess we can continue with the talk and continue discussion after the talk.
Yes.
Yeah. So
I'm just done with the talk. Almost. That's it. I was just talking about how we change the input parameters in EUHFORIA in the coronal model. We changed the PSP source surface radii. And why we did that? Because when we were actually doing the simulations at lower heights, that is 2.6 or 2.7 solar radii, then there might be a possibility that we are cutting the close magnetic field lines, and that's why we are getting the low density. And that's why when we go to the higher PSP source surface radii, from 2.9 solar radii further, then we can actually manage to reach the order of the measured in-situ density. So this is just to show the comparison, like what we did before and what we, after the changing the input parameters, what we got. So we managed to decrease the discrepancy between the model density at PSP position, but we still have a very large distance or the different order of radio densities, and also the model density at the radio sources. So all these colored lines are the model density at the different radio sources, so at different heights. And these are also very underestimated with the radio densities. So this still needs to be studied and to see what is the reason behind that. So to just conclude my talk, we created a catalog for type 3 radio burst observed during the first 8 PSP perihelions. We did the catalog for that. And 2 groups of type 3 radio burst observed on 5th of April 2019 were studied in detail. The radio source positions obtained using radio triangulation provided us the density profile along the burst propagation path. And due to the complexity in the time profile of the burst, the discrepancy was observed in the estimated radio sources. And this topic I'm studying in detail. The in-situ density from PSP were then compared with the radio observations, which showed the larger scale difference between the two. And the density at radio source position modeled with EUHFORIA were underestimated compared to the observed densities. To decrease the discrepancy between the observed and model density, we did the simulations at different piezo source surface radii from 2.6 to 3.0 solar radii, and we managed to decrease the discrepancy when we did the simulations at 2.9 and 3.0 solar radii. So this is not the complete study, so we need to study it further. And what we need to do is the statistical approach. So I have already triangulated like 10 more type 3s, and we just need to figure it out with the EUHFORIA right now. And also we are studying only with the stereo events. So the older events where we have stereo A observation and stereo B observation, to see that what we get from there as well. And we are also aiming to study the type 3 radio bursts which are passing by PSP spacecraft. So for now, whatever type 3 we have on the 5th of April 2019, they are not exactly towards the PSP spacecraft. So they are close by. So it's like indirect comparison. So to see, to have direct comparison, we need to see maybe the Langmuir waves in the dynamic spectra, or to identify the Langmuir waves, so that we know that the type 3s are approaching PSP, and then we can have a direct comparison. So that is also one thing that we have in mind to study further. So many more things we have to do, and this is not the end of this study. And thank you all for listening to my talk very patiently. Thank you so much. So we can have questions if anyone has.
Thanks, Ketaki.
Thank you, Ketaki, for this very nice and interesting work. So I guess we already had a very nice discussion in between the talk, but the floor is still open for the further questions. And I think there are still some questions in the comment box which we have not addressed yet. So I think I see one question from Mugundan. So Mugundan, can we just go ahead and unmute yourself to ask the question?
Oh yeah, let me find out what.
What is the angular resolution you'd?
Yeah. So what is typically the angular resolution that you would get with these goniopolarimetry measurements? And if you did, and attached to that, another question was if you are able to like trace the path of the sources through this method, and also I think you would also have in-situ measurements of the plasma density from PSP itself. So why not use that in EUHFORIA directly?
And yeah, that also we need to do. Like I just started my PhD with this work, so I need to do a lot of things. So this is just initial work, so I haven't actually done. Yeah, but that is also one thing that we have in mind. Yes.
But with the goniopolarimetry, what is the typical resolution that you would get there spatially?
I am not sure like about the resolution. Maybe Yasmina can say more about it.
Yeah, in principle, it's difficult to talk about the angular resolution. So the goniopolarimetry or direction finding observations is actually you have the antennas and on each of the antenna, the two antennas, you are getting the signal the signal which accounts for the electromagnetic emission. It's actually the change of the charge, which will basically give you the idea where there is electromagnetic emission coming from. So it does not have the angular resolution. It depends how frequently in time you collect it. So it has a temporal resolution, but it can come from wherever. So you see, it's difficult to say that to attach the point of angular resolution to it.
Okay, thank you.
Yeah, this is why in principle it's difficult if you have a signal which is coming from the two. There was one question related to that, two nearby regions. So if you have beams which are at the high frequencies, then these two nearby regions are like encompassing a smaller area, and you will get a mixed signal, but from this smaller area. As the beams are diverging, the area from where the signal is coming is increasing. So also your kind of double signal area is increasing, which makes the signal coming from the larger area and not giving you too good results.
So I see that there is a comment saying that the angular resolution is determined by the directivity, but then given that I presume that you would probably be using dipoles for this kind of measurement, like just cross dipoles. So in that case, then you're seeing like all over the sky. So which means you would in principle like be having sources anywhere from the solar disk, and you would have just triangulated it to the solar disk in effect.
Yes, you can have a source from wherever it is coming.
So in the earlier slide, I think Ketaki was making an attribution to an active region on the sun. Was it because only because it was, I think 2019 was relatively quiet, and that was the only active region that you made that association, or?
Yes, there were like two active regions. One was on the visible side, that you can see from the SDO, and one you can see from the stereo, which was like slightly behind the eastern solar limb. And the active region which was slightly behind the eastern solar limb was the responsible for these type 3. So they generated some jet-like structures which might have accelerated the electrons and generated some radio emission. But this was mentioned in the other paper that I mentioned also, like Wang et al. 2023. They also mentioned about this, that this active region actually produced some type 3s.
Okay, thank you.
Many type 3s that was studied in India. Yeah.
Okay.
I do see a next question from Anisha, but I think Yasmina has already answered that.
Yes, and it was also kind of similar to what Mohandan asked. So it's done. Thanks.
Yeah, thank you. Is there any other questions? Like, I have a question, like, Ketaki, for this event, do we have do you have observations of like radio spectropolarimetry? I think where like you can have the image of the radio sources and you can pinpoint the.
Yeah, even in PSP also we can observe like if they have some polarization or something. You are talking about the polarization, right?
Like
if they are polarized or not.
You call like where you can image the radio source on the sun, like some Gauri Vidanur images we have.
Yes, so yeah, that is also one thing that we need to do further. So I will be doing the imaging part with LOFAR to just like trace the this type 3s further towards the sun, because now I am actually observing or tracing their path in the interplanetary region. But of course, you can go towards the sun and observe in a higher frequency. So of course we have like Gauri Vidanur Radio Observatory, then we have LOFAR, we have MWA. So with all those, but for those observations, we can only get the radio sources in 2D. So with this method of radio triangulation, we can get the 3D radio sources. So we can trace the 3D path of the type 3s.
And is it like all the way from the radio source to the PSP, you can like track the radio source?
If it is going towards the PSP, right now, like I don't have that diagram over here, but yes. So the type 3s are going in one direction, and PSP is just like beside that. So it's not exactly in the same position as the type 3 propagation path. So that is why I said like indirect comparison, because it's not exactly at the PSP position. So that is one thing that I need to study for. That's why I said like the type 3s that going towards the PSP, that is also one thing we need to study. But for that, we need to observe Langmuir waves in PSP. And also when I started the study, it was an active, quiet period of the sun, and we didn't have much type 3s. And also now the stereo spacecraft is very close to the Earth. So we don't have nice separation between the two spacecraft, which is not favorable for radio triangulation. So many restrictions with that.
Okay, thank you. And I guess one question from Atul. Is there data on directivity fluctuation time series?
Directivity fluctuations.
Can you?
What
So
do you mean by
yeah,
that?
I can. So I was just wondering, like you say about these locations, right? So how
Yeah.
I'm not familiar with these
Yeah,
observations.
direction finding
So
data. Yeah, it's a
do
publicly
you have a
available.
yeah?
It's publicly available now, just recently actually. So it was not available publicly before that, but now both like stereo and stereo, you can find it on this CEDAW web page, where we can have all the spacecraft data. So you can find the direction finding data of stereo there. And for wind data, we have it on this Paris Observatory's website. On that, we have wind data available. But yes, both of the spacecraft data is available publicly now.
Yeah. Okay. Thanks.
I don't see any more questions there. So if there is not any more questions, so let's again thanks to our speaker. Then I would like to end the meeting here. So have a nice rest of the weekend, everyone, and
Thank you very much.
we'll soon meet in the next talk. Thank you. Thank you, everyone.
Thank you.